So in our previous example, we got the general solution to this equation of motion for this problem with the forced motion. And what we're going to do now is get the particular solution, and then we're going to graph everything. And so we look at the problem, and the problem tells us initially that we're 2 feet below equilibrium. All right, so that tells us right away that x at 0 is equal to 2. And then it also tells us that it's released with an upward velocity of 1 foot per second. So that means x prime at 0 is equal to -1. All right, remember upward is the opposite of gravity. And so we're going to go down and we're going to put those back in to our general solution. All right, you probably recall that we got this as our general solution, x prime at t. So we're going to have to find the derivative. It's going to be -6c1 e to the minus 6t minus 2c2 e to the minus 2t minus 1/2 sine 2t. We have a chain rule going on there. And then finally plus cos 2t. So we have another chain rule, so we have to multiply both the sine and the cos by 2. Alright, so now we're going to substitute. We had 2 for x of t, and we had -1 for x prime of t. And when we substitute 0 back in, good things are going to happen. So when we substitute 0 back into this term, e to the minus 6t goes away, e to the minus 2t goes away, and then sine completely goes away. And the only thing we're going to be left with is just this 1/4 as well as c1 and c2. So we get c1 plus c2 plus 1/4. Alright? And then we have to go through and substitute 0 into the other equation. And in our other equation, when we substitute 0, we're going to be left with -6c, -2c2. So -6c1 minus 6c2. And the sine term is going to go away, and the cos just becomes +1. Alright. And so let's go ahead and solve. It might be easier for us to do this by adding the constants to the left-hand side. So if we do that, we're going to get +7/4 equals c1 plus c2. And then -2 is going to be equal to -6c1 minus 6c2. Alright, so let's see. If we were to go through, oh, I'm sorry, I made a copy error. This should be a -2 on the x prime. Otherwise, we'd have parallel lines, and that probably wouldn't be good. So give me 1 sec, let me erase these. Apologies. Alright, so it's -2, and then this is going to be a -2. Alright. So let's multiply the first equation by 2, and we can solve easily. So if we multiply by 2, we get 7/2 equals 2c1 plus 2c2. And then -2 equals -6c1 minus 2c2. Now we can add the equations. And this is going to wind up being 3/2 is going to be equal to -4c1. And we can clearly see that -3/8 is going to be c1. Alright, so that one's not too bad. So we get -3/8 equals c1, and now we can just substitute that all the way back up into this first equation to make it really nice and easy on us. And so we get 7/4 is going to be equal to -3/8 plus c2, and if we add 3/8 to 14/8, that's going to be 17/8 equals c2. And so that's good. So now we're going to go ahead, finish this off, and get our equation of motion. Alright, and we can just literally copy this guy down. So I'm going to see if I can copy this and then That way we can just go through. There we go. Copy it down here. Actually, I'll copy right here. Nice. And I'll just move it a little bit. So we don't have to write the whole thing out. C1 is -3/8. And C2 is 17/8. So we get -3/8 e to the -6t, and then 17/8 e to the -2t. Alright, so that's our equation of motion, finally. And then from here, what we'd like to do is we'd like to be able to graph those. Alright, so, and we also have to identify the transient solution as well as the steady state. Okay, so the transient is going to be the first part of this, the -3/8. So we can say x at t. Actually, I'll call it t at t, just so we don't redefine x again. So I'll just call this t at t is going to be -3/8 e to the -6t plus 17/8 e to the -2t. And the steady state is going to be 1/4 cos 2t. So I'm going to call this s at t. So that's 1/4 cos 2t plus 1/2 sine 2t. Right? So, and the transient again is the part that comes from the general solution from yc. All right, so this is from yc, and remember, eventually that's going to go away. Right? The steady state eventually is going to be from yp, and eventually that's going to govern the equation of motion. Right, so finally we just have to plot everything. So I'm going to go ahead and insert my plot. And I'm going to cut this so that way we can see the whole thing. Alright, so let's paste it down here. Alright, and so here's our equations. Alright. The transient solution is the one in red, and of course, just like all the other graphs, we're not going to worry about anything to the left of the axis. So just pretend that doesn't even exist right there. And so the transient solution is the one that kind of starts out having the biggest influence over the equation of motion. And you can clearly see that the black and the red lines, up until maybe around 1, they exhibit almost the same behavior, all right? And then they start kind of diverging from there. You'll also notice that the steady state and the equation of motion, the one in light blue and black, after like right around maybe 1.5, they start converging, and then they really start laying on top of one another around 2.25 seconds, and they almost become the same function. And at some point, we notice that the transient solution just kind of has this behavior where it kind of just levels off and the value is almost 0. In fact, it's probably so negligible that we don't even notice it. All right, and you noticed in the solution we had like an e to the -6th power. So you can imagine even at 1, that becomes almost 0. So this is a pretty good indicator of how this force motion usually works. There's usually that transient sort of activity that goes on from the damping and from acceleration, etc. And then eventually the steady state solution, or the particular solution from the driven motion, is going to govern what happens with this.